So let's say I have a quantum system. Let psi be the state of the quantum mechanical system. Okay, and let A be a Hermitian operator. A be a Hermitian operator corresponding to some power. So I have a system in which state psi, and suppose if I measure this property A, that means measurement means I am actually making a measurement using a meter, classical operators. So when I make a measurement of A on this, I do not know, this is what I am saying is what quantum mechanics says, I do not know what will be the result of the measurement. But what I know from the structure of quantum mechanics is, since this is a Hermitian operator, its eigenstates become a complete orthonormal basis for the inverse space. So this psi can always be expanded in terms of Cn phi n, okay, over n, where this phi n are eigenstates of this A. Okay, so when I do a measurement, what I am guaranteed is that the result will belong to the eigenvalues of A. One of the eigenvalue of A will come out as my result, but which eigenvalue will come, I do not know. I cannot predict it. But what I can predict is what is the probability of each eigenvalue to come. That is what I can predict. So here, if I measure A, I can say that we get the result as one of this set An. That's what we get. We get the result as one of the set An. We do not know which one I will get, but we only know that it belongs to that set. The result will belong to that set. So you completed the measurement. You got the result. Okay. So let's say we got Al as the result. The first problem of quantum mechanics is this indeterminism. We do not know which one we will get. No predictability is possible. The second problem here is, after you get this result, the state collapses to phi n. It was initially psi. After you do this measurement, after getting this result, the state will collapse to phi n. State will collapse to phi n. We also do not understand what is the mechanism of this collapse. Okay, so this is another black box. We do not know what happens, but state collapses to phi n. Now after this, if you make measurement of A again, that is measure A again, what do you expect? Because phi n is an eigenstate of A with eigenvalue Al, I will get exactly the same A. Okay, so we get A. After that, state also will not change. Okay, but now suppose if I make a measurement of some other operator B, measure B, some other operator B, and then after that I measure A again. Measure A, what will I get here? In between I made a measurement of B, then I am again measuring A. Will I get A? Some other eigenvalue eigenvalue of A I will get. But is there a possibility that I get AL under some circumstances?
B and B commutes.
If A and B commute, I will again get AL. If A and B don't commute, then that state is disturbed by B again. So the disturbed state has to be re-expressed as a linear combination of A's eigenstates, so I will get some other eigenvalue. So if I measure A, we get AL if A and B commute. That's all the quantum mechanics is. This is what is contained. All the postulates, all mathematics, everything is only this. This is the conceptual summary of quantum mechanics. The measurement of B will not disturb the state if A and B commute. If A and B don't commute, this will disturb the state. And then you will not get this A value. You will get one more eigenvalue. Now you read any quantum mechanics topic, if you keep this in mind, everything you will understand what they are doing. Because rest is only mathematics. Since we did a lot of mathematics, if you understand this, rest is only a matter of detail. How to do this, how to operate this, how to get this, eigenvalues, eigenfunctions, and so on. And yesterday someone was pointing out during feedback session that solving h psi is equal to E psi is equivalent to diagonalizing the Hamiltonian. I am sure now you understand why. Because diagonalizing a matrix, as I told you, is finding a basis in which the matrix is diagonal. And that basis is the basis of eigenvectors. So if I want to diagonalize the Hamiltonian, I must find a basis in which Hamiltonian is diagonal. That is essentially eigenstates of Hamiltonian. So h psi is equal to E psi gives you set of states that are eigenstates of Hamiltonian, and in the eigenbasis, H will be diagonal. So diagonalizing the Hamiltonian is same as solving h psi equal to E psi.
You can give example to this as measuring the Bohr radius. Measuring the Bohr radius of 1s electron.
Basically, measuring the Bohr radius is measuring the position of the electron, because position operator is a Hermitian operator. So you assume that proton is at 0, measure the position of the electron, then that gives you the Bohr radius. Okay, so I will stop.